developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
My AFRL Hub project is to investigate the impact of shockwave boundary layer interactions on surface heating, and in particular, what if the surface was thin like a flight vehicle and that surface heating caused the panel to bulge and thus impact the fluid flow that's causing that heating.
When you place the cone flare in high-speed flow, you have a bow shock that forms at the nose tip, you have a boundary layer that develops in the conical forebody, and it thickens as it approaches the cone flare junction. Under certain conditions, the boundary layer may separate, and you'll have a separation shock. Boundary layer eventually will reattach on the flare, and you'll have a reattachment shock. And in between separation and reattachment, you have a recirculation bubble that can be unsteady. Downstream of the reattachment shock wave on the flare, the pressure is extremely high, and the boundary layer is relatively thin, so you have higher thermodynamic heating on the flare.
This coupled problem is known as a fluid thermal structural interaction, and it's a complex challenge impeding our progress to successful hypersonic vehicles.
This is a brief recap on our studies of the effect of surface deformation on hypersonic transitional shockwave boundary interactions on the Rotex-T cone flare. The schematic shows the characteristics of a flare-induced shockwave boundary layer interaction. The boundary layer under these conditions here separates prior to reaching the cone flare junction. The separation shock forms. It reattaches onto the flare, and a reattachment shock forms, downstream of which there's high aerodynamic heating. This high heating can be a serious issue for flight test vehicles and can even result in thermal buckling in certain cases. Representative deformation fields were simulated using a thermal structural model in Abacus finite element software. The test article consists of a 7-degree half-angle cone, 20-degree half-angle flare. It was tested in 2 facilities, the AFOSR Notre Dame Large Mach 6 Quietal and the AFRL Mach 6 Ludwig tube. For the experimental setup in both facilities, we collected off-wall and surface measurements simultaneously. The surface measurements consisted of infrared thermography, while the off-wall measurements consisted of background arctic Schlieren and high-speed self-aligned focusing Schlieren. Direct numerical simulations were performed to study the effects of the surface deformation. Here are experimental heating results from the Notre Dame facility. You can see on the top left, no deformation results in axisymmetric flow, as you can see from the uniform heating distribution. While with a deformed pedal, the flow breaks down from axisymmetric on the conical forebody to 3-dimensional on the flare. Centerline heating profiles are shown on the bottom half of the slide, separated on the cone and the flare. We see that a larger deformation results in higher peak heating along the centerline on the flare. Here we have a facility comparison. The top half of the slide is showing the effect of the flare deformation on maximum heating. We can see there's much larger changes in maximum peak heating as Reynolds number increases compared to a undeformed flare configuration. On the lower half, show the effect that surface deformation has on the separation bubble size. We see that a larger deformation field results in a smaller separation bubble length. Self-aligned focusing Schlieren measurements are shown here. The elevated peaks on the top 3 plots indicate the presence of dominant modes. The mode shapes are plotted for each deformation in the lower half of the slide. We can see that the similar mode shapes indicate that the deformation had negligible impact on the dominant off-wall instabilities. Here we have the experimental results compared to the direct numerical simulations. The top half represents the undeformed flare configuration, and the bottom half is the deformed flare.
Our research into the effect of surface deformation on hypersonic shockwave boundary layer interactions on the Rotex-T cone flare proved to be highly successful. It was an effective collaboration with the Air Force Research Lab. Subject matter experts provided guidance into the most valuable problem to study. They connected us with ATA Engineering, who contributed an analysis that enabled us to design the test article. Researchers at Ohio State University performed direct numerical simulations, which are high-fidelity computations that yielded insight into the complex physics of this flow field. Lower fidelity computations would not have arrived at such useful results. At Notre Dame, we performed experiments that enabled the measurement of the surface heating and density field with high spatial and temporal resolution. These results were found to agree very well with the direct numerical simulations. They also agreed well with experimental results obtained at the Air Force Research Lab. The success of this project has led us to identify a fruitful avenue for future research. We plan to replace the solid-walled test article with one with a compliant panel, which will be an even better simulation of hypersonic flight. However, it will be even more complex as the surface deformation will be coupled with the flow field and the heating rate that it endures. I look forward to continuing this research in that vein.
The AFRL Hub project has led to several key findings pertaining to the effect of flight test-inspired structural deformation on the aerodynamic loading associated with shockwave boundary layer interaction. Based on the completed analysis, buckling of structural panels promotes the transition to turbulence, moves the separated flow region closer to the cone flare junction, and increases the peak heat flux. These findings will influence the structural design of high-speed aerospace vehicles. The most notable and intriguing findings are that deformations on the flare can influence the flow far upstream on the vehicle, and that the peak heat flux is strongly dependent on the free stream noise environment. Beyond the technical contributions, this project has resulted in the development of several PhD students and new research collaborations between AFRL and professors at Notre Dame and Ohio State University. This has led to several larger scale research proposals for future collaboration. Completion of this work has improved our fundamental understanding of the effect of structural deformation on aerodynamic loading.